Hey friends, Ben again. This is a video for vector calculus. We're talking about evaluating scalar surface integrals. So remember that you just went through this super long video for Tuesday where we talked about parameterizing surfaces. I think that does a fairly good job of trying to figure out how to do this whole thing of parameterizing surfaces, okay? Now we come to the reason why you parameterize them. You parameterize them so that you can evaluate these surface integrals in a fairly organized way. So remember how you had to have that magnitude of your r prime of t in your line integrals? So that's going to be like a length or a speed there. And so now with surface integrals, what we've got to think about is not having an infinitesimal piece of length, but rather an infinitesimal piece of area. Okay, so that's a little bit cumbersome, but play along with me a little bit here. Now, I've taught this material out of like 50 different textbooks, and I don't remember which one we've got. I'm sorry. And it's kind of been a long day too. However, what I need you to spot is that I'm trying to organize this in the easiest consumable way. Oftentimes, there's something in the textbook where they will do an extra bit. Where there's just extra crap put in there. And the way that I'm trying to tackle it is meant to skip that sort of thing. So let's take a look here and see how this goes. All right. So we've got some scalars, or we've got some surface that we're talking about. And it's going to be defined by some r vector of uv. And if you take a look at the picture here, the notion I've got is that we've got a tangent plane at some point. And that tangent plane we can find by evaluating the r vector's derivative with respect to one of the variables and another of the variables. And what that will give you is actually something, two vectors that lie in the plane. If you take the cross product of those, then you'll get the normal vector to the plane, okay? So keep that in mind. It's going to show up again later. But notice what I've written here, that when you take the magnitude of that, you're going to get this magnitude of RU, magnitude of RV, sine of theta, which is the area of a parallelogram. But the parallelogram we're going to be thinking about, the du and dv on them, is going to be infinitesimally sized. So, so if you were doing a surface integral of just ds, it would be adding up all of the infinitesimal pieces of area. If you get a function in addition to that, maybe those pieces of area have density, maybe they are carrying a point charge. There's something that you're adding up from them, okay? So when we talk about scalar surface integrals, there's just some scalar quantity that's associated with each little piece of area. So we're going to try evaluating one here, and you're going to see the process of it. And I'm going to try really hard to make it the same process every time. And that way it's fairly mechanical, really. So we're evaluating this x plus y ds. And if you take a look over here, I've gone ahead and parameterized something for us. And in order to work with this, we're going to have to find out what r sub u is. And that's going to be cosine v sine v 3. And then we'll have to find out what r sub v is. And that's going to be, let's see, minus u sine v, u cosine v, and 0, okay? And then you're going to have to do R sub u cross R sub, my handwriting, R sub v. And we're not going to take the magnitude immediately. We're going to do that as a separate step. And I have written this in the way that I have so that you can kind of visualize as we go along. We're going to do the I part, which means we have to take these here to multiply together in order to get our entries. So sine v times 0 is 0 minus 3u cosine v. All right. And then we're going to have to do 3 minus u sine v, and then minus 0 cosine v. So minus 3 u sine v. Okay. And then on the last one, u cosine squared v minus a negative u sine squared v. So we will end up out of that just getting a u, right? Now the magnitude of RU cross RV is going to be a square root. And notice that we will have 3u cosine v squared and 3u sine v that will square. So when we square those and put them together, we can just get 9u squared plus u squared. So that means, is that right? Yeah, that means that we have a square root of 10 times u, okay? Because the u values we're talking about are going to be positive. So that means that we can drop the absolute value portion of it. So that's not too horrible. Now, when you're doing these, you're going to go, oh my God, no, oh my God, no, oh, it's horrifying. But the problems that I've given you have been designed so that the integration is not too bad, okay? Some of them, the algebra is pretty bad, but they're meant to not be horrifying integration. Ask me about that in class, and I'll say more. So we'll have an integral, and now our x plus y. The x is just u cosine v, and the y is just u sine v. And then we need to put in this magnitude. So we have a square root of 10 and a u and a du dv. I got to write that right. Now notice right here, we have a rectangular region. So we can go du dv and hit say 0 to 2, and the dv is 0 to pi. And we don't have to worry about anything. But if your region's not rectangular, you actually have to stop and maybe draw a picture and figure out what to write for it. So once we get to that, we can go ahead here. I'm going to leave the 0 to pi sitting outside. And you know what, as a matter of fact, I'm going to let me just move that out of the way and put my square root of 10 right there. And then I'll put that integral there. And then we're going to be integrating u squared in both of those positions there. So I'm just going to factor that out and have my cosine v plus sine v like that. And then have my 1/3 u cubed that goes 0 to 2. And then the dv. And so I'll have a square root of 10 over 3 here. And, and plug in, I guess, 8 minus 0. So maybe that would look nicer too. Maybe that would look nicer if I wrote it as 8 square roots of 10 over 3. Okay, went through that pretty quick, but it shouldn't be too rough for y'all. So integral 0 to pi of cosine v plus sine v dv. And then when you integrate cosine, what do you get? Sine, and then the sine, it's minus cosine. And we're going 0 to pi. So you plug in the pi first, And you get, what is the sine of pi? 0, and then minus, and then the cosine is -1. Okay, and then minus, and now we plug in 0, sine 0, 0, minus, and we plug in cosine of 0 is 1. So you end up with 16 square roots of 10 divided by 3. Okay. Ugh. Answers look awful. Anything that has to do with arc length, surface area, it feels like the answers are always awful. So, all right. This is another one. Here we're trying to deal with the portion of 2x plus 3y plus 4z equals 12 in the first octant. Yeah, but this means that since we're trying to find a mass, that we are going to end up integrating this piece right here, ds. So I'm going to write double integral across the surface of x squared plus y squared ds. Okay. And then it may help for us to do a quick sketch on this, right? So in doing this sketch, I'm just going to have to think about setting x and y equal to 0 and solve for z, and similarly for the other bits. And so I'm going to hit here a 6 out here on the x-axis, and on the y-axis of a 4, and on the z-axis it'll be a 3. So I will have, actually, I think I can get my drawing program to try to shade that in. Yeah, it did. Cool. So you've got a triangular piece instead of a rectangular piece. So with regard to this, you need to think about the two vectors that you're going to deal with here. If we're going from 6, 0, 0 to 0, 4, 0, then we have to go down by 6, up by 4, and leave our z's the same. And this one here, we have to go down by 6, leave our y's the same, and go up by 3 in the z direction. So that means that our r vector of uv, we're going to think about starting at that point 6, 0, 0, and have 6 plus. Now we're going to have to do u. I'm going to have u be the one that goes towards the v0, 4, 0. So I'm going to put a -6u. And then for the v, I'm going to put a -6v. And then the y direction, I'll neaten this up here in just a second. Sorry. The y direction will have the 0 plus 4u and plus 0v. And then the z direction, we will have 0 plus 0u plus 3v. So that is going to be 6 minus 6u minus 6v, 4u, 3v. Okay, looks pretty messy. Now here is the deal with it. We are going to go ahead and say our u goes from 0 to 1, and then our v goes from 0 to 1 minus u. You can reverse those, and that's totally fine. All right. Yeah, there's something real quick I want to point out here. When you have to parameterize these yourself, if you had reversed which one was u and which one was v, when you did your r sub u and your r sub v portion, then you would end up reversing those, and your cross product would go the opposite direction. Later, when we talk about flux integrals, you have to keep track of which direction that you're going. And so if you reverse u and v, you'll get the negative of what you were supposed to get otherwise. Some of the examples that we have for that, I struggled to make sure I had my my geometric portion of it set up right. Okay. All right, but anyway, trying to keep this mechanical, we are going to figure out r vector sub u, which is super easy. it's just the minus 640, and the r vector sub v is just going to be the minus 603, okay? You can do those mechanically from looking at the function that's sitting right over here, but you could also see it just from the two vectors that we have. All right, so when we take r u cross r v, then we're going to end up getting 12, and then let's see, 18, and then 24. So the magnitude of r vector u cross r vector v is going to be equal to, oh shoot, I got to go get a calculator to do it, sorry. 12 squared plus 18 squared plus 24 squared is 1,044. Is that a perfect square? It is not. Okay. So square root of 1044, and that's going to be 6 square roots of 29. That's kind of ugly, but you know, it's doable. All right, so we're going to set up our integral here. And on the outside, we have to put our u going 0 to 1, and on the inside, our v going 0 to 1 minus u. Okay, hope that doesn't get too awful. And then we're going to have to deal with x squared. Oh, that does turn out to be awful. 6 minus 6u minus 6v squared. And then the y part is just 4u being squared. And I'm seeing that I don't have room to write this all out. So I'm going to have to go to a second page, which I had hoped not to do. But, oh well, 6 square roots of 29, and then dv, and then du. All right. So, as mentioned, copy it, add another page, paste it, put it up there. Okay. So, in trying to simplify out, we have algebra to do, but it shouldn't be terrible algebra. However, I am seeing that I ought to take and pull stuff out to the front that there's no need to have hanging around. Notice that with this part here, you can spot a factor of 6 to come out of the whole thing, so we might as well say 36 times, and then we have to square it. Gosh. So if I have 1 minus u minus v squared, I have to think about 1 minus u minus v, and then minus u plus u squared plus uv, and then minus v plus uv and plus v squared. I know that's terrible, but it has a 1 and a minus u and a minus v, and nope, minus 2u minus 2v, and plus 2uv, and then plus u squared and plus v squared. Yeah, okay, and I hope it does not offend y'all that I'm going to just drop that part out, and then I'll have the plus 16u squared, and then we'll say dv du. Okay, can we do anything nice? I can see a factor of 4 that we can take out of everything and have 24 square roots of 29, integral 0 to 1, integral 0 to 1 minus u. And I am going to distribute through here and have 9 minus 72u minus 72v plus 72uv plus, okay, we have 36u squared and another 16, so 52u squared, and plus 36v squared, dv du. So 24 square roots of 29, integral 0 to 1, 9v minus, no, I'm not going to do that the hard way. Notice everything that does not have a v in it, you can just say you need to multiply by 1 minus u. It may not actually be all that great of a help, but all right, then the 72v is going to be 36v squared. We'll plug in the 1 minus u and square it. And the 72uv is going to be a 36u and v squared, and we'll plug in the 1 minus u and square it. And of course, subtract 0. And then the 36v squared, you will have a 12v cubed, and then plug in the 1 minus u and cube it. And then have d derivatives. All right, so this is the time when I'm going to hit pause because you don't need to watch me. Oh, except I can't pause while I'm sharing screen. I'm going to pause and just do the arithmetic because hey, friends, I'm sharing again. I hope I'm sharing again. It looks like I needed to hit the share button in order to share. Okay. All right. All right. After a bunch of just messy arithmetic, if I didn't get the arithmetic right, I'm sorry, but okay. So as you run along here and integrate these, because they are just powers of u, you end up being able to do something kind of nice with them. You'll have the minus 15 is being integrated against a constant, so we'll just have 1 minus 9 times, since it's a first power, we'll end up with a 1/2 plus 124 times a third minus 28 times a fourth. And so we end up with 24 square roots of 29. And I cannot do the rest of the arithmetic in my head. So I am going to do it on a calculator and get 89 over 6. Seems like a weird number to get, but okay, fine. The 6's will cancel out, and then you'll have 4 times 89, whatever that is, square roots of 29. Boom, we're done. Okay. So the answer we got was super nasty, but we were just dealing with a polynomial, you know. So, all right, here's something that's a little bit more interesting in the setup. And I got to tell you the truth that if the integration gets too nasty, I will just turn over to Symbol Lab and let it do it for me. So we've got the cone 4 minus the square root of x squared minus y squared. So if you drew a quick sketch of this, it would look somewhat like that. And with the z being given to us so that it's greater than or equal to 4, it's going to go from the tip down to the base. Okay. Now, if you went ahead and subtracted 4 on both sides and squared, you'd see this as z minus 4, the quantity squared equals x squared plus y squared. And that should resemble a little bit these cones that we did some parameterization for before. So with our r vector of of UV, I am going to treat the U as though it was the R and the V as though it was theta. If you would prefer to go ahead and write R and theta, you can, but in that case, you had better use a different variable for, for your R vector that we have out of the front. Okay, so I'm going to say U cosine V, U sine V, and then the Z ends up being just a U. Okay. Because of the fact that we're only doing stuff that's down below that 4, the subtraction there, I can say something about our U. Oh, and I messed that up. Let me fix that. Oh, great. Come on. That should have been 4 minus U. Okay, because yeah. Anyway, though, then I'm going to let my U's go from 0 to 1 because I have the subtraction. If I'd made it addition, then I would have made it minus 1 to 1 or minus 1 to 0 instead of 0 to 1. And because I want to do the whole circle, the V will go 0 to 2 pi. If you prefer to go minus pi to pi, you can certainly do that. Okay. All right. And I think maybe I will take my picture and put it down here, put this next to the picture, and stuff like that. Kind of push it up here. It's sort of out of the way. All right, so the density proportional to the distance from the origin. So that means that we're going to do our surface integral, and the density is proportional. So it is some k times the distance from the origin, so x squared plus y squared plus z squared, and then multiply that by the ds. Okay, so we've got to figure out the r vector sub u, and this should feel familiar. And minus 1, and the r vector sub v minus, minus u sine v, and then it's u cosine v, and then 0. Okay, and the ru cross rv. Oh gosh, we have 0 minus negative, so u cosine v goes here. And then for the other one, we end up with a u sine v minus 0. And then for the last one, we end up with a u cosine squared v minus a negative u sine squared v. So this turns out to just be a u. So when we take the magnitude of ru cross rv, and we're just taking and squaring everything, adding them up, we should end up with a square root of a u squared from the u squared cosine squared and u squared sine squared, and then another u squared here. So we get an extraneous square root of 2 hanging on, and a u. All right. Let's see how bad this one turns into. So I'm going to leave the k hanging out front there and do my integration inside. And now x squared is going to be u cosine v squared. Y squared is going to be u squared sine squared v. So I'm going to go ahead and write u squared there. And then plus the z is 4 minus u squared. And then the ds, you pick up a square root of 2 and a square root of 2u. And then a du dv. The u's went 0 to 1, and the v's went 0 to 2 pi. Okay. The v's all vanished. That's super. So 2k pi sits out at the front there because we're just integrating that out. And then we have to integrate 0 to 1. Oh, so 4 minus u when you square it we end up then with a 2u squared, and then a minus 8u and a plus 16. Oh, and I just noticed we can also take and have this be 2 square roots of 2. I can just jam that out to the front as well. All right, so 2 square roots of 2k pi. And we are integrating 0 to 1 again, and it's just a polynomial. So we can say 2 times 1/3 minus 8 times 1/2 plus 16 times 1. And I hate it when I can't do this stuff. So it is going to be 8 plus 2/3. And so that's going to be 26/3. So 52 square roots of 2 k pi over 3. Like I said, every one of them is going to turn out to be pretty nasty. But anyway, let's see. Do I want to do this next one here? Yeah, it's probably a good idea to do one more. Okay. So this one here, if you see your surface that you've got here is a paraboloid, then that lets you say that your r vector is going to be equal to just a u cosine v again, a u sine v again, and then the z turns out to be u squared. So when you do the r sub u, cosine v sine v 2u, and the rv minus u sine v, u cosine v, and 0. This should all feel super duper familiar. Oh, let's start to do the magnitude all at once. I need to do RU cross RV first. So I end up getting minus 2 squared cosine V. Well, that's not encouraging. And then minus 2u squared sine V. Well, that's a little bit better because those will go together. And then for the other part, I end up getting, let's see, u cosine squared V plus u sine squared V. So we end up with just a u. So the magnitude RU cross RV square root of, we will end up with a 4 u to the 4th plus u squared. Oh Lord, I hope that that didn't turn out to be too awful. You can see that you can take a u out of that and then end up with a square root of 4u squared plus 1. Now, if the xy over z, if that all cancels out, this looks like this might not be too terrible. So your integral that you want to do here, we're going to say x times y. Well, that's going to be u squared cosine v sine v, and then divided by z. Well, z is going to be u squared. Oh, well, that's nice. And then times u square root 4u squared plus 1, like so, and then d something. Sorry. I guess I'll go du dv, right? And the u values were like the r values here. And so those were going to go from 2 to 4. And the v were like theta, so those are going to go 0 to 2 pi. Try not to get super worried about this because this looks like it's going to have something funny happen. Cancel those out, and we have an integral 0 to 2 pi cosine v sine v dv. times the integral from 2 to 4 of u square root 4u squared plus 1 du. Now, this integral right here is going to be a u substitution. And since we got a u already, I guess we could say w substitution. It's one of my favorite stupid jokes. But we're not going to bother to do it. You know why? Because we are integrating cosine v sine v from 0 to 2 pi. That is a period of it. So that means we will get 0 times who cares. So really, I probably should have had something else on this problem, like x is greater than 0 or something like that to make it turn out to not be super boring. But sometimes when you're doing this integration, you get to take advantage of little tricks like that. The one about integrating from 0 to 1, the x to the n power turns out to get you 1 over n plus 1. Use the hell out of that because it's going to come up. The fact that you integrate sine or cosine through its period, that cancels out and gets you 0. Use the hell out of that too. Okay. But some of them, well, all the ones that I've given y'all for problems for Thursday are stuff where the integration is not too terrible. One of them, you need to do a u substitution where the u is the stuff under the square root, and then the stuff that's not under the square root, you have to solve for. And if you're saying, screw that, I'm going to go use Symbolab. Guess what? Symbolab just says, no, not going to do it, which mystified me. But anyway. All right, so I will see you all soon. Take care.